This presentation is on charge at different pH, and so we sometimes call this protonation state. And so here we're interested in what the charge is on whether we have the carboxylic acid or its conjugate base. This is the acid-base reaction. You've seen the arrows for it, so I'm just showing you here. You should be able to do these very easily. You should be able to identify the acid, the base, the conjugate base, and the conjugate acid. So the pKa of this acid is about 4. It's 3.77. I usually say that I usually work with whole numbers, so I would call it 4. So the Ka is 10 to the minus 4. We can draft up the equilibrium constant for this, the expression, and so this is the product of the concentrations of the products divided by the product of the concentrations of the reactants. You've seen this before. The KEQ is going to be about 10 to the minus 2. I'll tell you why in just a second. And that's because if we multiply both of the above expression by the concentrations of water, which is constant in this case, it's 55 moles per liter. So we multiply KEQ times the concentration of water. We multiply the right side of the expression by the concentration of water. And the concentration of water cancels out in the numerator and denominator. But this concentration of water times KEQ, we define that to be Ka. And that Ka is in fact 10 to the minus 3.77 or 10 to the minus 4 if we want to be more exact. That is where we get the pKa. Actually, we got the pKa by taking the negative log of the Ka. We'll talk about that a little bit more in the next couple of slides, but that's what you should have learned from general chemistry. So in aqueous solution, the pH ranges from 0 on the low side, which is very high acidity, to 14 on the side where we have very weak activity. And recall that those mean that the H plus concentration is between 10 to the 0 molar, which is 1 molar, or 10 to the minus 14 molar for those two numbers. So the pH and the H plus, you should be able to go back and forward between these two. You should also recall some ideas from Le Chatelier. If we added HCl to the above reaction, that's the same thing as adding H3O plus, and so the H3O plus concentration increases. And if the H3O plus concentration increases, the pH decreases. And so pH is decreasing when concentration of H is increasing, something you should have seen in Gen Chem as well. But if we added H3O plus to the above equilibrium, that would shift the equilibrium to the left according to Le Chatelier. If we added sodium hydroxide to the above expression, that would mean that the H3O plus concentration is getting smaller because the sodium hydroxide would neutralize the H3O plus, and that would mean the pH goes up. And so the equilibrium, according to Le Chatelier, is shifted to the right. How much is the equilibrium shifted based on a change in pH of 1 unit? That's something we'll talk about in the next couple of slides. And what is the protonation state at a specific pH? So that means the following. If we look at the above expression, the protonation state on the left side is we have the acid protonated. On the right side, it's deprotonated. That is, the conjugate base lost the proton. And so, the protonation state is either neutral or negative in this particular case. And so we'll use that kind of language. Not a heck of a lot, but a little bit. So this is the same reaction, same arrows as we've seen before. Let's draft up the Ka that we did before. The only thing I'm doing differently here is I'm separating out the H3O plus concentration as a separate factor on the right-hand side. Otherwise, it's identical. You should go back and look at this if you're not sure. This is exactly the same thing as the last slide. We're going to do this for a reason. Let's take the negative log of Ka, and we're going to take the negative log of the expression on the right side. So it's the negative log of the ratio of the concentration of the conjugate base to the acid. So those two concentrations minus the log of H3O plus. And so we took the negative log of the entire expression and we split it up. This is what we get. Now we're going to do the following. I'm not going to change at all the middle portion of this, which is the negative log of the ratios of the concentrations. As I've mentioned before, that's exactly the same. But on the left side now, I'm going to say, oh, the negative log of Ka we define as the pKa. And on the upper right-hand side, the negative log of the H3O plus concentration, that's the pH. And so pKa equals negative log of the concentration, the ratios of those the concentrations, conjugate base on top and acid on the bottom. And so those are so we get this expression plus pH. And then we're going to make the following thought process. We can shift the equilibrium to the left or the right depending on changing the H3O plus concentration the way that we described on the last slide. So let's shift the equilibrium so that the carboxylate, that is the conjugate base, is the same concentration as the carboxylic acid. Another way to say that is the carboxylic acid, the acid up above, is half deprotonated. Half of it's now conjugate base. Those two are at equal concentrations. And when that's true, then the negative log of the ratio of those concentrations, the ratio of the concentrations, by the way, becomes 1, and the negative log of 1 is 0. 10 to the 0 equals 1. Negative log is 0. Okay, so we've shifted the equilibrium. Now the acid and the conjugate base are in equal concentrations. Now look what happens. So the middle ratio, the negative log of the ratio of the concentrations, that became 0. pKa now becomes pH. So pH equals pKa when the conjugate base and the acid are in the same concentrations. I'm going to say that a couple of different ways because I want you to digest this. When those two, the acid and the conjugate base, are in identical concentrations, then that's the pH at which is the pKa of the starting material. Or if you have the pH equal to the pKa, the conjugate base and the acid are in the identical concentrations. And so let's box around the left. When the acid and the conjugate base are the same concentration, that's when pKa equals pH. So let's look at the above expression. The carboxylic acid there is pKa of around 4. That means at pH of 4, it's half acid, half conjugate base. That's what this information tells us. And so let's put it a little bit more formally. When the acid concentration equals the conjugate base concentration, that happens when pH equals pKa. But also when pH is the same as pKa, the acid and the conjugate base concentrations are equivalent. They're identical. So again, for formic acid, pH equals 4. At pH of 4, the conjugate base and the acid are in identical amounts, and essentially the acid is half deprotonated at that pH. So in summary, we've done some analyses for the acids. Remember that these are aqueous, and so the pKa's are between 0 and 14, and know that we can get from pH of between these ranges as well. If the pKa equals pH, then the concentration of acid equals the concentration of the conjugate base. If the acid concentration equals the base concentration, then pH equals pKa. And so those are, you need to know these backwards and forwards for these. And so if pH is less than pKa, the acid is greater. And so go back and look at the last expression. If you increase the if you increase the amount of H3O plus, which is the same as decreasing the pH, then you're going to shift the equilibrium to the left, and the acid is going to be the concentration of the acid is going to be greater. If pH is greater than pKa, the conjugate base is going to be in greater concentration than the acid is. We can calculate the ratio of acid to conjugate base if we know pKa and H. We're going to do that in the next slide presentation. I will tell you now that the above is important for biochemical functional groups, phenols, ammoniums. We're going to see these in the next slide presentation, but it's important for you to know how to